Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to picture a cosmic engine.
Okay, a cosmic engine.
Yeah, but not just any engine. I mean, something so incomprehensibly powerful that its energy output easily outshines, like 10,000 of our own suns.
Which is already pretty hard to wrap your head around.
It really is. And the craziest part is that the object driving this blindingly energetic mechanism is, paradoxically, completely defined by its absolute darkness.
Right. It remains one of the most compelling paradoxes in astrophysics, honestly.
Yeah.
You have this entity defined by an event horizon, which is a boundary where space-time is so severely warped that the escape velocity exceeds the speed of light itself.
Right, so nothing gets out.
Exactly. Yet the environment immediately surrounding that boundary is responsible for producing, well, some of the most violent, brilliant displays of power in the entire cosmos.
And today we are looking closely at one of those displays. We're talking about Cygnus X-1.
A class.
Yeah, for anyone who follows the history of astronomy, that name carries a ton of weight. I mean, this is the system that famously prompted a bet between Stephen Hawking and Kip Thorne back in 1974, I think.
Yeah, 1974. Hawking actually bet against it being a black hole, mostly as a sort of, scientific insurance policy.
Right, like if he was wrong about his life's work, at least he'd win a magazine subscription.
Exactly. But he eventually conceded because the observational evidence just became completely overwhelming.
So what we're looking at is a binary system. It contains the first confirmed black hole humanity ever found, and it's locked in this brutal gravitational embrace with a massive O-type supergiant star.
It's an incredibly extreme environment.
It is. But the reason we're talking about it today isn't just for the history.
No, not at all.
A recent study published in Nature Astronomy, led by an international coalition of scientists and spearheaded by researchers at Curtin University, they actually managed to definitively measure the instantaneous power of the jets shooting out of this specific black hole.
Which is a huge deal. I mean, measuring jet power dynamically, like as it's actually happening, that required a complete methodological shift in how we observe high-energy phenomena.
Says we've known about these jets for a while, right?
Oh, yeah. Identifying the presence of a jet in the radio spectrum is pretty standard procedure at this point.
Okay.
But calculating its power output and clocking its velocity in real time while it's being actively deflected by, stellar weather, that is a monumental leap in observational astrophysics.
So let's get into the mechanics of that stellar weather, because I love the term the lead author used for this. Dr. Steve Prabhu coined this phenomenon, dancing jets.
It's a great visual.
It really is. So we have the black hole, which is sitting around 21 solar masses, and it's orbiting this supergiant star.
Yeah.
And the environment they're sharing is just incredibly hostile.
Extremely hostile.
Because the primary force driving the chaos here isn't just gravity, right? It's the stellar wind coming off the supergiant.
Right. So O-type supergiants are massive. They are incredibly luminous and extremely hot. And because their luminosity is so intense, the radiation pressure pushing outward from the star's core actually physically overcomes the star's gravity, particularly in its outer layers.
So it's literally blowing itself apart with light.
Exactly. It drives what we call a line-driven wind. The star is essentially shedding millions of times more mass than our sun does with its solar wind. It's blasting this constant, dense, high-speed stream of plasma out into the surrounding space.
And the black hole is sitting right in the crosshairs of that plasma stream, right? Actively accreting mass from that supergiant's wind.
Right in the middle of the storm, yes.
But wait, let me stop you right there. We need to clear something up about the mechanism of these jets, because I think it trips a lot of people up.
Sure.
By definition, an event horizon means nothing escapes, not even light.
Correct.
So how on earth is a black hole forcefully ejecting a massive jet of plasma out into space at relativistic speeds? If nothing can cross back over the threshold, where is this material even coming from?
That's the key right there. The material in the jet never crossed the event horizon.
Oh, really?
Yeah, it never made it inside. The jet is generated by the extreme magnetohydrodynamics of the accretion disk itself.
The accretion disk being that swirl of material falling in.
Exactly. As the black hole pulls plasma from the supergiant's stellar wind, that material doesn't just fall straight down, it has angular momentum.
Right, it's spinning.
So it spirals inward, forming this really dense, flattened disk of superheated plasma around the black hole.
And because that plasma is an ionized gas, it's carrying its own magnetic field lines with it as it falls in, right?
It is. And as that plasma spirals closer and closer to the event horizon, it accelerates to a significant fraction of the speed of light.
Wow.
And the innermost region of that disk is subject to extreme frame dragging. We call it the lens-Thirring effect.
Wait, frame dragging? What does that mean?
It means the rotation of the black hole itself is actually pulling the physical fabric of space-time around with it.
That is just mind-boggling. Space-time itself is twisting.
Yeah. And the magnetic field lines threaded through this plasma get dragged along, twisted, and tightly wound up by this differential rotation.
So it's kind of like taking a thick rubber band and just twisting it relentlessly. The kinetic energy of the spinning disk is being converted into magnetic tension.
That's a perfect way to look at it, and it keeps twisting until the tension reaches a breaking point.
And then what happens?
The magnetic fields become so tightly coiled that they collimate, meaning they form this tight, vertical funnel perpendicular to the accretion disk.
Okay.
The extreme tension basically acts like a magnetic slingshot. It captures a fraction of the infalling plasma just before it crosses the event horizon and violently blasts it outward along the rotational axis.
Wow.
So the jet is powered by the rotational energy of the black hole and the inner accretion disk, not by anything escaping from inside the event horizon.
Okay, that makes so much more sense. So we have these highly collimated beams of relativistic plasma shooting out from the poles of the black hole, but they aren't shooting into a vacuum.
No, definitely not.
They're firing directly into that hurricane force stellar wind radiating from the supergiant star we talked about.
Which brings us right back to the dancing jets.
Yeah.
Dr. Prabhu's term perfectly captures the fluid dynamics at play here. We are basically watching a high-velocity, low-density plasma jet slamming into a lower velocity but incredibly dense stellar wind.
Okay, let me try an analogy here. Think of a high-pressure water fountain in a public park. Right?
Okay, I'm with you.
If a severe gale rolls through, the column of water doesn't just shoot straight up. The lateral force of the wind intercepts the stream and bends it sideways. If you've ever walked past a fountain on a stormy day and gotten misted, you've experienced the micro version of Cygnus X-1.
That's exactly it. The wind alters the trajectory of the water based on the ratio of their respective forces.
Right. So in this system, the black hole is the fountain, the supergiant's radiation-driven plasma is the gale force wind, and the jet is the water stream.
Spot on. And as the black hole completes its 5.6-day orbit around the star, the angle of that stellar wind hitting the jet is constantly changing.
So from our perspective on Earth, what does that look like?
Well, the radio-emitting particles in the jet appear to sway and bend back and forth, altering their angle depending on where the black hole is in its orbital phase.
That is wild.
Yeah, the physical structure of the jet is actually deformed by the ram pressure of the stellar wind.
But, okay, visualizing a cosmic fountain bending in a stellar storm is one thing. Actually observing it from, over 7,000 light years away? That's an entirely different problem.
It is a massive headache, observationally speaking.
Because our largest single-dish radio telescopes, even massive ones like the Green Bank Telescope or the Parkes Observatory, they can't resolve something this small at that distance, can they?
No, they can't. At that distance, the entire binary system, the wind and the jet, just blur into a single, unresolved pixel of radio emission.
And you can't just slap a bigger lens on a telescope to fix that, right? It's a physics limitation.
Right, you are constrained by what's called the Rayleigh criterion.
Okay, hit me with the physics.
It dictates that your angular resolution is proportional to the wavelength of light you are observing, divided by the diameter of your telescope's aperture.
Okay, so the bigger the wavelength, the bigger the telescope you need.
Exactly. And radio waves have very long wavelengths compared to visible light. So to get high resolution in the radio spectrum, you need an impractically large dish.
Like continent-sized.
Pretty much. So the only way the researchers could resolve the minute deflection angle of this jet was to utilize very long baseline interferometry, or VLBI.
Oh, right. So instead of building a single dish the size of a continent, you use multiple existing radio telescopes scattered all across the globe.
Yes, it's a brilliant workaround.
You observe the exact same target at the exact same time, And you use the physical distance between the telescopes, which is the baseline, as your effective aperture size.
Exactly. By linking telescopes across the United States, utilizing the Very Long Baseline Array, they synthesized an Earth-sized virtual telescope.
That is just incredible.
But the technical challenge of VLBI is staggering. You aren't just pointing dishes at the sky.
What else goes into it?
Well, you have to record the incoming radio waves at each individual station with incredibly precise timestamps. And I mean precise. They use hydrogen maser atomic clocks.
Oh, wow. Just to make sure they know exactly when a specific wave hit a specific dish.
Right. And then you have to physically ship those hard drives to a central supercomputer.
Wait, physically ship them? Like in the mail?
Yeah, because the data rates are often way too massive to transfer over the internet, so they mail them to a central supercomputer called a correlator.
Okay, so what does the correlator do once it has all these hard drives?
The correlator lines up those atomic timestamps, accounting for the microsecond differences in when the wavefront hit each telescope on Earth, and it interferes the signals to reconstruct a high-resolution image.
Wow. So they basically stitched together an Earth-sized telescope.
They did. And that synthesized resolution allowed the team to actually see the jet structure. They could map the exact vector of the jet and measure the precise angle of deflection caused by the stellar wind at different points in the orbit.
And this is where the physics of the measurement becomes highly elegant, I think. Because it's basically just a conservation of momentum problem, isn't it?
That's exactly what it is.
Because the researchers already had constraints on the properties of the supergiant star, right? So they could calculate the ram pressure of the stellar wind, meaning how much lateral force the wind was applying to the jet.
Right.
So if you know the force pushing from the side and you use your Earth-sized interferometer to measure exactly how much the jet bends, you can just calculate the momentum flux of the jet pushing forward.
You've got it. The deflection angle gives you the direct ratio between the wind's power and the jet's power. It allowed them to calculate the instantaneous power of the jet.
Instantaneous?
Yes. And Professor James Miller-Jones, who is a co-author from the Curtin Institute of Radio Astronomy, he emphasized just how critical this instantaneous measurement is compared to our historical methods.
Okay, let's talk about those historical methods. Because usually, if we wanted to know how powerful a black hole's jet was, we had to look at the macroscopic damage it did to its environment, right?
Right, the aftermath.
Like, we looked at the massive radio lobes or cavities that the jets carved out of the surrounding interstellar medium over time.
Exactly. You measure the volume of the cavity, you estimate the pressure of the surrounding gas, and you calculate how much mechanical work the jet had to do to push all that gas aside.
But the issue there is that it only gives you the time average power of the jet over, like, hundreds of thousands or even millions of years.
Right, it's a huge time scale.
But let me stop you there because that time scale discrepancy is really interesting. Cygnus X-1 has been accreting matter and firing these jets for a very long time. So if we are trying to understand the broad strokes of how this black hole operates, why is the million-year average insufficient?
That's a fair question.
Like, if I want to understand the thrust of a commercial jet engine, looking at its total fuel consumption over a long flight gives me a pretty good baseline of its efficiency, right?
Right, but that's assuming a steady burn. And a black hole's accretion process isn't a steady commercial flight. It is highly variable, chaotic, and bursty.
Oh, okay.
A better analogy for this engine would be testing the thrust dynamics of an experimental scramjet. If you only look at the total fuel consumed over its lifetime, you learn absolutely nothing about how the engine responds to a sudden, extreme fluctuation in air density in a specific millisecond.
Because the accretion disk isn't perfectly smooth. I get it. So clumps of denser plasma are falling toward the event horizon, creating sudden spikes in friction and temperature.
Exactly. Which manifest as intense, rapid flares of X-ray emission. And we can observe these X-ray flares happening in real time. But if our only measurement for the jet is a million-year average, we cannot correlate the two.
Because you're comparing a real-time event to a million-year average.
Yes. We can't see how a sudden influx of matter signaled by an X-ray flare translates into a change in the jet's power.
Oh, wow.
But by utilizing the wind deflection method to calculate instantaneous power, the team can finally measure the jet's output at the exact same moment they observe the X-ray emissions from the infalling matter.
So they can dynamically link the fuel intake directly to the exhaust output.
Precisely. It's a game changer.
Okay, so they captured the snapshot. They ran the vector calculus on the deflection angle. Let's talk about the numbers they extracted from this because they are staggering.
They really are.
The calculated kinetic power of the jets in Cygnus X-1 is equivalent to the total luminosity of 10,000 suns.
Yeah, 10,000 suns. And that is just the mechanical energy channeled into the jets. It is a highly focused, tightly collimated beam of plasma carrying the energy equivalent of 10,000 main sequence stars.
That is terrifying, honestly. And the velocity measurement is equally impressive because determining the speed of relativistic jets without obvious moving clumps or knots, I think they call them, to track has historically been a massive headache.
It's notoriously difficult.
But the team determined the jet in Cygnus X-1 is traveling at approximately 0.5 c, half the speed of light.
Right. Roughly 150,000 kilometers per second.
Just to put that in perspective for you listening, at that velocity, the plasma would reach the moon from Earth in just over 1 second.
It's fast. And pinning down that velocity allowed the researchers to finalize the most crucial calculation of the entire study, the accretion efficiency.
Okay, break that down for us.
When you calculate the mass accretion rate, meaning how much matter is actually plunging toward the black hole, and you compare it to the instantaneous power of the jet we just talked about, you derive what we can refer to as the 10% rule.
The 10% rule.
Yeah.
Yep.
Dr. Prabha's research confirmed that approximately 10% of the rest mass energy of the infalling material is extracted and channeled directly into the jets.
Okay, we definitely need to contextualize that 10% figure.
Oh, for sure.
Because it's easy to look at a 10% conversion rate and assume the engine is highly inefficient. Like, if my car only converts 10% of its fuel into forward momentum, the rest is mostly wasted as heat. That's terrible.
Right. But in astrophysics, it's the exact opposite.
How so?
The conversion of rest mass into energy via black hole accretion is actually one of the most ruthlessly efficient processes in the universe.
Okay.
Think about nuclear fusion, the process powering our sun and every other star. Fusion converts roughly 0.7% of its mass into energy.
Wow, less than 1%.
Right. But a black hole accretion disk can reach radiative efficiencies of up to 40% depending on the spin of the black hole.
40%, that's a massive jump.
It is. The sheer gravitational compression and friction liberate a huge fraction of the plasma's rest mass energy, dictated by Einstein's EMC2.
Okay, so out of that total liberated energy, 10% is captured by the magnetic fields and accelerated into the jet.
Exactly. And because of EMC2, 10% of the yield from an accretion disk represents an almost apocalyptic amount of kinetic energy being violently deposited into the surrounding interstellar medium.
Okay, so 10% is actually a massive cosmic return on investment.
Oh, absolutely.
And this specific fraction, this 10% rule, is not just an interesting piece of trivia for Cygnus X-1. The research emphasizes this heavily. This fraction is kind of the linchpin for modern cosmology, isn't it?
It really is. When astrophysicists run cosmological simulations to model the formation of the universe, or the cosmic web, and the evolution of galaxies, they rely on complex hydrodynamic code.
Right.
And baked into that code for years has been an assumption.
An assumption about this 10%.
Yes. They assumed, based on theoretical models of magnetohydrodynamics and some indirect observations, that black hole jets carry away roughly 10% of the accretion energy.
So they just plugged that number in.
They had to. They needed that specific feedback mechanism in the simulations to make the virtual galaxies evolve into something that actually resembles the real universe we observe.
What happens if they don't include that 10% energy injection from the central black hole?
The simulations fail. The virtual galaxies would just keep cooling gas and forming stars endlessly. They would grow too massive too quickly. The simulated universe wouldn't match reality at all.
Wow. So the models literally required that 10% assumption to work.
They did. But confirming that theoretical value through direct dynamic observation of a living black hole system has been incredibly elusive.
Until now.
Right. The Curtin University-led study finally provided the observational proof. It anchored our mathematical models to empirical reality.
And that concept of an anchor point is exactly how Professor Miller-Jones framed the importance of this discovery.
It's a great term for it.
Because, think about it, we're looking at a stellar mass black hole here, around 21 solar masses. But the black holes at the centers of galaxies, supermassive black holes or active galactic nuclei, those are millions or billions of solar masses.
Right, completely different scale.
But the fundamental physics of the accretion disk, the magnetic field twisting, the mechanism launching the jet, It scales invariantly, doesn't it?
It does. The equations governing general relativity and magnetohydrodynamics in these systems do not fundamentally change just because you increase the mass parameter.
So a supermassive black hole operates on the exact same blueprint as Cygnus X-1.
Exactly. Cygnus X-1 essentially acts as a cosmological Rosetta Stone.
That's brilliant. We spent decades developing the VLBI techniques, observing the X-ray flares, and mathematically untangling the wind deflection of this relatively close 21 solar mass black hole.
Yep.
And now we finally translated the instantaneous mechanics and confirmed the 10% conversion rule. So now we possess a verified translation key that we could apply to the supermassive engines driving the evolution of distant galaxies.
Engines we could never hope to observe with this level of localized detail, yeah.
It's credible.
And the timing of this verification is critical too, because observational radio astronomy is on the verge of a massive paradigm shift.
You're talking about the SKA.
Yes, the Square Kilometre Array Observatory. The paper points directly toward it. It's currently under construction across Western Australia and South Africa.
And for anyone who hasn't heard of the SKA, it isn't just another telescope. It's a generational leap in interferometry. We're talking about thousands of dishes in Africa and up to 1 million low-frequency dipole antennas in Australia.
The scale is hard to comprehend. The data processing requirements alone will rival the entire global internet traffic.
And it's just nuts.
But the sensitivity and resolution of the SKA will allow astronomers to detect radio jets from active galactic nuclei across millions of distant galaxies, peering deep into the universe's past.
So we will have this unprecedented catalog of supermassive black holes actively feeding and firing jets into their host galaxies.
Exactly. But as you know, observing 1 million jets is just cataloging.
Right, it's just stamp collecting at that point.
Right. To understand the life cycle of those galaxies, astronomers need to know exactly how much mechanical energy those jets are dumping into the circumgalactic medium. This is the process of AGN feedback, or stellar feedback.
Let's talk about that feedback, because a galaxy's ability to form stars is governed by the temperature of its gas reservoirs, right?
Yes. Cold, dense molecular clouds collapse under their own gravity to ignite nuclear fusion and birth new stars.
Okay.
But if the supermassive black hole at the galactic center is firing a relativistic jet carrying 10% of its accretion energy into the galaxy's halo, the kinetic energy of that jet drives massive shock waves through the gas.
And those shock waves heat the gas up.
Exactly, dramatically increasing its kinetic energy and preventing it from collapsing. It physically quenches the galaxy's star formation.
Wow. It just shuts down the star factory.
It does. Or, alternatively, under specific density conditions, the compression from the bow shock of the jet can actually force gas clouds to collapse, triggering a sudden, localized starburst.
So the jet acts as the galaxy's primary thermodynamic regulator. It can turn star formation off or force it into overdrive.
Precisely. You cannot accurately model the life and death of a galaxy without quantifying that feedback mechanism.
But when the SKA comes online and observes the quasar's jet 1 billion light years away, scientists won't need to resolve the microscopic fluid dynamics of its local stellar wind to understand its power, will they?
No, they won't. And that's the beauty of it. Because the international team behind this study researchers from Curtin, Oxford, the University of Barcelona, the University of Wisconsin-Madison, the University of Lethbridge, and the Institute of Space Science, they already did the grueling foundational work on Cygnus X-1.
So the SKA astronomers will just be able to observe the X-ray luminosity of the distant quasar's accretion disk, apply the confirmed 10% rule derived from Cygnus X-1, and instantly calculate the thermodynamic impact that jet is having on its host galaxy.
Exactly. We calibrated the instrument we need to decode the evolution of the cosmos. It connects the microscopic physics of a localized plasma interaction right to the macroscopic structure of the cosmic web.
It's just a phenomenal journey when you step back and look at it. We started by looking at a violently unstable supergiant star, shredding its outer layers through radiation pressure to create a dense stellar wind.
Right.
Then we saw how an Earth-sized interferometry network managed to capture the precise deflection of a relativistic plasma jet plowing into that wind.
The dancing jet.
The dancing jet, yeah.
Okay.
And through the vector calculus of that deflection, the instantaneous power of the black hole was finally clocked at 10,000 solar luminosities, moving at half the speed of light.
Which ultimately proved that 10% of the incredibly efficient accretion energy is diverted into the jet. That confirmed a fundamental assumption of cosmological modeling and really set the baseline for the next era of radio astronomy.
It fundamentally changes how we view astrophysical chaos. The turbulent, violent interaction between a supergiant's wind and a black hole's jet isn't just noise obscuring the physics.
Oh, the turbulence itself was the key.
Exactly. The turbulence contained the exact mathematical variable needed to understand how galaxies grow and die. And I think that leaves us with a really profound, lingering consideration regarding the nature of complex systems.
Oh, absolutely.
If the localized fluid dynamics of a single binary system hold the mathematical constraints for the evolution of the entire universe, it raises the question, what other fundamental constants of reality are currently hiding in the plain sight of chaotic, localized phenomena, just waiting for the resolution of our instruments to catch up to the math?